So I feel honored that I can give the first lecture of this wonderful conference. And about 1 year ago, the organizer of this conference asked me, Vivian Baradi and me, to give a mini course in this conference. And we are very happy to accept it. But later, when we discussed about the content of the lecture, we feel some difficulty to give some consistent 6 lecture in this conference. So what we decided is just we give 2 basically independent mini courses as one course for transfer operator. And basically, I'm going to give 3 lectures about some very basic part of the theory. And then maybe Vivian will give some more advanced stuff. And first of all, I have to say that I changed the title of my talk. So title is just a little. So transfer operator for Anosov flows. This is announced by Xiaobo, but actually I want to change it to a diffeomorphism. Actually, maybe with respect to the purpose of this conference about beyond hyperbolicity, maybe we'd better to discuss about Anosov flow, because this is one example of a partially hyperbolic dynamical system. But on the other hand, I'd like to discuss about some basic idea in this considering transfer operators. And for this purpose, I think it's better to insist on this simpler setting. So I decided to decide this change of title. So let me first introduce a few results that Vivian and I got about 10 years ago. So, and this is the result that I'm going to speak about. So the situation is actually, I discuss about uniformly hyperbolic system, not beyond. Okay, so F is Anosov diffeomorphism, so C Anosov diffeomorphism. So we assume that there exists a decomposition like of a tangent bundle like Tm into EU plus ES, or EU plus ES, and some number larger than 1, such that, so it is preserved, this decomposition is preserved, and df EU, okay, and inverse. So the action on the cotangent, unstable bundle is expanding this way, and then df ES is bigger than 1. Okay, this is the situation we are going to consider, and then we consider the transfer operator for this. As you all know, the dynamics of this diffeomorphism is very complicated, and it's difficult to trace all the orbit. So instead of, sorry? Oh, sorry. Yes. And okay, this is. Sorry, this is. Okay, and then so instead of tracing, considering each orbit, we consider some mass of orbit and action of flow diffeomorphism on them. So this is given by transfer operator. So operator. This is L. Maybe this is an action of function on M and defined as follows. So L U X equal multiplication by some function G X, then push forward. Like, sorry, this is F minus 1X. And here, G is a smooth function on M. Okay. This is the operator that we are going to consider in this lecture. Then the result, this is, oh no. Yeah, U is a function. So, yes, so we take some function U here, okay? Then you get another function, LU. And this LU is defined this way.
So G is some fixed function.
Yeah. So maybe the position is not very good. Maybe this is here, right? So we multiply U by some function G, fixed function, and then push forward by the flow, by diffeomorphism. So we consider this action, and maybe we like to capture the property of dynamical system by looking at this operator. For example, looking at the spectral property of this operator.
So you mean if L depends on G?
Yes, L depends on G.
Yeah, also depend on G. So sometimes we fix, okay, let's G to just 1 or some, okay, derivative of F. So we can consider many situations. But here we only, okay, suppose that we are given some function G. Okay, then okay, and also actually this is obtained by Planck, Keller, Liberani, and maybe also I have to write cell. So what we found is that in some function space, this operator have a discrete spectrum. So maybe we can write this. So for any R, there exists Hilbert space or Banach space like HR. And okay, sorry. This contains smooth functions and contained in the space of distributions. Such that this operator L extends to HR boundedly and has discrete spectrum on this region. This like CFG lambda 2 minus R. So the spectrum of this operator acting on HR look like this. So there's a small core, and the bound. This is CF. Okay, maybe it depends also on R. No. This is not. FG and lambda minus R. And on the outside, we have only discrete eigenvalues with finite multiplicity. G? Yeah. Dependence on G?
Yeah, the capital G there. It doesn't look like a linear operator now.
G is not an operator.
Yeah, G is a coefficient. Yes. So, okay, this is the first result that I want to speak about. And another result is that another result shows that this discrete spectrum is in some sense intrinsic. So let me see. Okay, this. Sorry?
What is a prime in the C infinity?
It's a dual, so it's a space of distribution.
Oh.
Okay. So and another result that I want to speak about is theorem B. Theorem B. Okay. So as n goes to infinity, we have the following asymptotic. So we consider something called a flat trace of Ln. This is actually defined as follows. This is the sum of the point, periodic orbit, periodic point, and here we have take some weight with some weight. So this is I minus df minus nx. And we have gn x. Here gnx is, as usual in dynamics, this is gx plus gfx plus g to the fn minus 1x. Oh, sorry, multiplication. Sorry, this is okay. And the asymptotic is the following. So this is like lambda I to the n, 1 to m, and plus O C F G to n. Here lambda I is OI. Okay, where? Okay. Those are eigenvalues. So I did something wrong. This we write it as lambda I. Okay. So the first inequality, this is just a definition. So actually, you can just ignore this.
So M depends on R.
Okay, this is something wrong. Okay, so where I had to write something small, introduce some small epsilon. Okay, so let me introduce some small epsilon here, right? Then, okay, we only have finitely many. And the epsilon is arbitrarily small.
But you never said what was G.
Sorry? Not? It's okay. G. Okay, then, so this formula implies that, so in the first theorem, you may think that the spectrum may depend on the choice of the function space. But with this, it is clear that this spectrum, lambda I, discrete spectrum is intrinsic, because the left-hand side is nothing to do with the function space. Okay, so So first remark I want to give is that so this spectrum lambda I is intrinsic. Maybe 2, the diffeomorphism F and the function G, right? Lambda i's, yeah. But this is that holds for any R, and also this holds for any R. So actually, if you take larger and larger R, then you will see more and more eigenvalues.
But for example, can you recover also Jordan blocks from irreducibility?
Yeah, for this I don't know. Yeah, but still, I think I can prove that the Jordan block is also intrinsic. I mean, the size of Jordan block. Yes. Yes, to take into no. Yeah, but that is not clear from this. Yeah. But anyway, so these numbers are intrinsic to, and maybe also the multiplicity is intrinsic to the flow, diffeomorphism, and the weight. Okay, and it is called Reuel-Policot resonance. Sorry, can I say it again? Yeah. The eigenvalues are on the outside of that circle. Okay.
And those are intrinsic or that circle is really small, right?
Yeah. You can take smaller and smaller, larger and larger, and then the circle becomes smaller and smaller. And from this, you will not see that when you take a smaller circle, you will there, okay, like this. So if you first observe some R, then you don't know what happens inside, but you have some eigenvalues inside. Then another R, you will get another picture. So like small circle. Then you will find some new resonances here, but these are independent. Just give me one.
All of them are intrinsic.
Or intrinsic, yes. Because
Maybe it's a good time to mention that the reason you can take R arbitrary large is because you assume that F and G are C infinity.
yeah, yeah,
And when they're
yeah,
not C
right.
infinity, then there are other results.
Yeah.
But then there is a limit. It's another
Right, right.
This is the family HR monotonic.
HR, which are?
Are they embedded when are those or diseases?
So, sorry, what? HR, no. Maybe I will explain this later, so you will see.
This is the way it's supposed to be, by the way. Constant interruption.
Okay, very good. Okay, so I want to explain about this result. Maybe you already have some questions, and so you will have some more. And maybe I want to explain about this result. And basically, I want to explain about the structure of transfer operator behind this result. So, and the idea is that, so we want to explain this result using some analogy to the so-called scattering problem. And another idea that I want to introduce is a wave packet transform. And actually, we are applying this idea. I'm working with Frederick Faure and using these ideas and apply it to Anosov flows. So if you are interested in, maybe you can look up my joint work with Frederick. Maybe that is still in archive and not published, but you will be able to find it. Okay, so this is the purpose of my talk. Okay, so we want to present this result and describe the structure of transfer operator behind this result. And what I like to follow is an analogy to the scattering problem. So let me describe what is the scattering problem. This one. So scattering problem is a problem about wave equation, but on the outside of some obstacle. So suppose that, okay, you are in the ocean and you imagine that there are a few islands. Okay? Then some wave comes from outside. Then you can imagine that there will be some interaction. And then after a long time, the wave goes in a few different directions. Right? And this kind of problem is called the scattering problem. And I don't go into the detail of this problem, but I just want to say that a few structure behind this problem. So first, if you consider the wave equation, and suppose that you consider some boundary condition on these obstacles, then you get some one parameter family of operator which describes the propagation of wave. Okay, And this is usually unitary operator. But on the other hand, you can simply imagine that if you start with some wave, suppose that almost all the place there's no wave, but in the neighborhood of this obstacle, some compact neighborhood, we have some non-trivial wave. Then what you imagine that what happens in the future, okay? Then maybe you can easily imagine that, okay, wave goes away after a long time, and there will be some decay of energy here. Maybe the wave will not remain very long time here. So this, but...
You mean that the wave kind of starts in a compact region?
Yeah. On the...
Dissipate outside?
Yeah.
Okay.
But since this is unitary operator, basically the norm is given by the energy. So, and by the, there's no energy loss in the wave equation. Actually, that energy is preserved. So we don't see any decay of energy. But of course, but on the other hand, we like to see how energy decays after a long time in this compact neighborhood. So one idea which I can found in the original work of Lux and Phillips, that actually in that case they consider the following way. So actually they constructed some subspace called closed subspace called, this space is called outgoing, and other space is called incoming. Okay, so the construction of this is not very difficult, and they prove that the following property. So D plus and D minus is orthogonal to each other.
D minus is incoming or outgoing?
Incoming. Yes. And second, for T becomes 0, we have that, okay, ut D plus is D plus. So once the wave is outgoing, then after some time, again the situation is outgoing. And ut minus T, D minus is D minus. And if you consider the intersection for all T of ut D plus, this is 0. And ut D minus R equals 0.
Is that R?
Yeah, for all R, but because of this, actually in this case, maybe we only have to consider positive time. Because if you go negative time, then it increases. So yeah, you can take it as a T larger than 0, and this is T maybe negative. And third, if you take union, ut D plus T in R, then it's dense in L2, so or the space of so like ut D minus T in R Okay, and so they introduce this structure in the problem.
So X is a Hilbert space, and it somehow.
Yeah.
We don't care.
Yeah, I don't like to care, but basically this is L2, R2 minus R, O plus W2 to R obstacle. Something like this. Yes. Then what they started to discuss, and one important operator that they consider is the operator Z. So UT induces some operator Z. What's it right? Z. This is like this. So the domain is first. We consider incoming state, but it's orthogonal. So it implies that the component of the function in X, but which have no component, incoming component. And then we divide it by d plus. So from these conditions, maybe from 2, maybe from 0 and 1, sorry, then we see that this is well defined. And so this is not completely trivial, but this is contracting. The T, U, goes to 0 as t goes to infinity. Maybe this follows from the condition 2 and the unitary property of ut. It's okay, so ZT is just an induced mapping on this space. And basically this describes the energy around this obstacle. So if we basically what we do this operator is that we cut off the incoming term and then look at how it decays. But at that point we just ignore the outgoing part. Okay, and the generator of ZT has, again, discrete spectrum. Maybe in this case, spectrum will look like this, or generate like this. And this spectrum will describe the decay of energy around the obstacle. Okay. Of course, this is nothing to do with the transfer operator, but what I want to explain is that actually, if you look at the transfer operator closely and you look things in the frequency space, you will find a similar structure like this. But before going further, I want to introduce a simpler model for this, because this model is too difficult for me. Yes, this is a book for this subject, and I cannot explain this. So maybe I like to escape to some much simpler case. So this is a model that, the scattering problem is a model that we have, but maybe for concreteness, I like to introduce another model which is closely related to this. So this is 1.2. This is a matrix model. For resonances. This is basically introduced by my joint worker, Frederick Foray, and let me explain it. So we consider two infinite matrices. Consider infinite times infinite matrix A, Aij, and K. Sorry, this is L0, and K is Kij. This is these two, L0 and K, are infinite matrix, but very simple one. So first, for the first one, L0, the entry is the following. So we have 1 when I equal j plus 1, and 0 otherwise. What is this? This is okay. Let me write that one. Kij. Okay, 1 0, and ij equals 0 0, and so this is a simple transfer operator on Z. So let us consider integers. So 0, 1, 2, 3, 4, minus 1, minus 2, and so on. Then we consider a translation. So this move from the right to the right. Okay. And this operation is expressed as a transfer operator, like a matrix L0 above, right? And we introduce another one. This is K0, K, and K is just a simple one. So here we introduce multiplication at the site 0. And we don't do anything on the outside. Just erase the other part. Okay. Yeah. Yeah. Sorry. Thank you. Thank you. This is I wrote right lambda. So yes, thank you very much. Yeah, I wanted to write lambda. Okay. And that is a matrix, and the corresponding transfer operator is like this. So L0 implies some translation, and K is a small perturbation. And sorry, this is, we said, sorry?
Lambda is greater than 1?
it doesn't matter, but basically I like to consider some small lambda because I like to say that this is a small perturbation of the whole thing. So oh, and we set L equal L0. So L0 is the one basic operator plus some compact perturbation. This is a situation we like to consider. Then maybe it is natural to set outgoing subspace like this, L2 and Z plus, or positive part of integer, positive integers, and D minus is L2 Z more than 0. Then we can find these properties, right, in discrete time. Then
What's X?
X here, okay. This is X is L2Z.
So what does L2 of Z greater than 0 mean?
Sorry, L2.
When you define D plus?
Yes. Yes. So what I mean is that
The entries are positive.
yeah, in positive part it takes value, and in negative 0, just 0.
Okay.
Yeah. So sorry, this is not a very clear thing, but so we regard that these two subspace these are the subspace of this one. Then, following the idea, we introduce the operator Z. This is D minus, then orthogonal, and divided by D plus. Okay? But this is actually just a simple C, and the operator induced by L is just a multiplication by lambda. So we find resonance lambda. In this setting. And this is a model that we have in mind to analyze the transfer operator for hyperbolic dynamics.
Okay, in this particular case,
Yeah.
L0 plus A.
Yeah.
Oh, that is unitary. I see. Because or is it not?
Maybe it is not unitary, but yeah.
I thought the shift might do something, but no, it's not actually unitary.
Yeah, L0 should be unitary, but yeah.
So it's a compact. But over here, you actually have a unitary situation, but then the map on the quotient is not unitary. Wait, so
Yeah, it should not be unitary, yes.
Okay.
And okay, I forget. But at this point, I want to warn you about this resonance, because this lambda looks like an eigenvalue, this is indeed so for this operator. But to observe this, we need this machinery, right? And for example, there's some subtle point for this. For example, if you consider this operator L, and you consider the inverse of this, okay, then you find some similar structure. But for that operator, you don't find lambda inverse as an eigenvalue. maybe if you like, you can compute the inverse and then try to see this. So to observe this resonance, you need some setting. And this is almost, of course, the setting is natural, then things look natural. But on the other hand, there are some subtle points about it.
These two examples are supposed to illustrate theorem A.
Yeah? Yes. This.
Theorem B.
No. Yeah. But still, okay. But at this point, I'd like to say that, okay, in this setting, this matrix setting, maybe it's natural to consider that trace of this operator is lambda, because we only have lambda on the diagonal, right? And this is the idea to that lead to theorem B. Okay. Okay, maybe this is good. Huh? Okay. So another remark is that, so in this model, we can find some resonance lambda. And basically, this is an eigenvalue for system. But without this structure, it's not, it is not legal to understand it as an eigenvalue. Because if you consider lambda as an eigenvalue, then corresponding eigenfunction or eigenvector will not be contained in this space. And one way to find resonance as an legal eigenvalue is the following. So for R equal to 0, we consider the following subspace, a space. So U, this is Z to C, and UR is e to the minus RK, UK square is infinity. So what I want to do is that, okay, we count basically the function L to Z is this is a space of functions on Z, right? 0, 1, minus 1, 2, 3, and minus 2. Then in this space, I like to introduce some weight. Like here we put e to the minus 3r. This is e to the minus 2r. This is e to the minus r. And 1, e to the r, e to the minus 2r, and not plus 2r. Like this. So we put some weight for each side and count the function with this weight.
Sorry, is this the norm or the square of the norm?
Oh, yes, I guess this square, yes. Then things become much easier. First, the operator L0, because we put this weight, actually, and L0 is just a translation to the right. So that operator is has small operator norm. So this is L0 and HR. This is equal to e to the minus r. And on the other hand, K, this is just a finite rank operator. So actually this is, okay, even this space, this is a finite rank. Okay, and in this case, we can observe lambda as an eigenvalue of this L to HR to HR. Sorry?
For R large,
Yes. If in this case e to the minus r is bigger than smaller than lambda. Yes.
But even if R is small, it's an eigenvalue.
Yeah, not in this space, I guess. Yeah. So with this, we set up some function space which includes the eigenvalues, and then find the resonance as an legal eigenvalue. Sorry?
Why is nothing
Okay, so
an eigenvalue, but it's not isolated. That's the problem.
but if you like to have an eigenvalue for lambda, eigenfunction or eigenvector, maybe this is 0, 0, and 1, and so maybe lambda minus 1, lambda minus 2, and so something like this. If you write down the eigenvalue, yes, eigenfunction, then this is not in the L2. Yeah, so we set up this weight to get to the vector into the space. Okay. So here I'd like to give one lemma. Let me write this lemma C. So suppose that this is an Hilbert space. And A is an bounded operator. And B is a finite rank. Or more generally, we can say that this is compact. But for simplicity, suppose that this is finite rank. Then A plus B has discrete spectrum on C bigger than A. And this is a very basic lemma that to obtain the discrete spectrum. And the proof is not too difficult. So if you consider the eigenvalue, we consider this invertibility of this operator, right? But then we can write it in this way: z minus zi minus a, and I minus zi minus a inverse b. Okay. And maybe we consider this, suppose that the absolute value of z is bigger than the norm of a. Then this is invertible. And if you look at this, then since b is finite rank, so this is identity minus some holomorphic finite rank operator, which depend on z in holomorphic way. So with this, we can find a discrete eigenvalue, because basically this is invertible if and only if this part is invertible. And of course, if you have B is compact, then maybe you can approximate that compact operator by finite rank operator, and you put the rest here, then you get the similar conclusion. And also, maybe you already realized we can replace this operator norm by the spectral radius. But anyway, we have this kind of lemma, rather easy lemma, and we get the discrete spectrum in theorem theorem A, using this lemma. Sorry? Oh, sorry. Oh, okay. I stop here. Sorry.